He loves solving problems, learning with others, and when not coding, Amos fly fishes and hikes with his family. Give it up for Amos.
Thank you. It's so good to be back here. I've been here at every Gig City, and have mostly just left you guys probably sad that you came and listened to me, but good to be here. So I want to start out with the title of this, Currently Afloat. So our benevolent hosts, Bruce and Maggie, there's Bruce back there, a few years ago, they have a boat called Currently Away. Do you still own the boat, or did you get rid of it? You don't own the boat. All right. So they also wrote a book about their adventure, so you should go on and get that. But it's just a little nod to them, to their trip that they took from here all the way out around the Great Loop, which goes into the Gulf of Mexico, Canada, back down the rivers, back to here. So it's pretty amazing. And they shared their story, and it's awesome. So go read that. All right. So I first gave this talk to a company after I sat for a week in a monastery with no computer. And so I had to hand draw my slides out of necessity. And after I gave the talk to them, I liked the aesthetic of it so much that I just added some more slides, cleaned up, moved things around, and kept it. And also because I wanted to fight against the AI revolution that everybody is deciding that they need to build their slides with AI. So mine was paper. I spread them out all over the floor and ordered them. So we'll see. We'll see where we get. So I do work for HCA Healthcare. I work on a project called Water Park. It is a distributed in-memory database thing. And here's what I'll say. I really don't do anything because it's built on the beam. It's been running for 5 years with 0 milliseconds of downtime, including in deployments. It has no database. Everything is in memory and kept in memory all the time. So it's kind of an amazing project and a lot of fun. But this isn't about that. You see, I had a friend, it was 2019, and Scott, who is the CEO and founder of No Inc., gave me a call. Scott had been an elections board director. He was an elections investigator for the state of Missouri at one point, and he really believes in democracy and getting people out to vote. And he saw a problem, and that was that people didn't want to come vote because they stood in line for too long. And he said, if I want more people to speak and put their vote in, I need to fix that problem. And Scott was really successful at fixing that problem. He was in 29 states, 900 jurisdictions, and was handling 1/3 of all voters in the United States. They also, I believe, are in Canada. This is 55 million people in a day that we process there. If you've been to vote here in the US and you might sign into a book, that's called a poll book, or if you scanned your ID, it's probably No Ink. So here's the problem. 2020 is coming around, and it's gonna be the biggest election of all time, according to Scott. And he was worried because they had a really big issue. They have 50,000 of these poll books reaching out to their server called ePulse and constantly syncing information with ePulse and with each other. And it was taking its toll on the server, because when you have 50,000 automated devices, you're basically doing a DDoS, a distributed denial of service attack, which is when a bad actor, usually a bad actor, but this time he's doing it to himself, is overloading your server so that you can't handle any valid requests. Or my favorite DDoS attack was when my kids were in the shower when they were younger, and they would be in there for way too long, and my wife and I would go to every sink in the house and turn on the hot water. Yeah. I have 5 kids, so I think there's more kid jokes in here. So I said, yeah, Scott, what do you have going on? Tell me about your system, what you have going on. Let's see what we can do. And he said, well, I have a whole bunch of servers behind a load balancer talking to a database, and it's got a couple of read replicas on there. And the 50,000 iPads are sending requests to this over and over, usually about every minute at least, and that's when it's just sitting there and nobody's using it. It's getting loads and loads of data, and it was all in Ruby too, so it did pay for some of us, right? Yeah. So he also had done a few things where he had certain areas that had their own set of servers, because like New York City and LA have more voters than some states. So different areas and regions of the United States had their own servers. I already mentioned the load balancer. This is my idea of a load balancer, is the person running the Ferris wheel, where they don't put everybody on the same side of the Ferris wheel. Although that might be fun to watch. I'm a little morbid, maybe. So I started thinking, like, what is going on with this system? What's the problem? This is what computers look like. Yeah, about right. Borderline. So this is me working at the computer trying to figure out what's going on. And I thought about two things. Systems need prevention and resilience. Those are like the two biggest things that drive my thought when I'm thinking of a system. So prevention, load shedding. See, who knows what load shedding is? All right. Okay. So I'm not wasting my time. Perfect. So load shedding is to prevent problems by increasing your throughput over time. So if you have a server that can handle 100 requests a minute, okay, it's really slow at that, but and you send in 110 requests, you start to back up after a while. Maybe your server goes down, right? Because you've overloaded it. Well, now, and maybe it takes a minute to reboot. Now you've lost 100 requests that you could be having processed. So in order to keep your throughput, you want to throw away 10 requests. Trying to convince somebody that the best way to serve their customers is to throw away their customers' requests is kind of it's a rough conversation. It took me, so I worked there like a year with them. It took me months to get them to get to load shedding, and then they still weren't on, and we implemented it 2 days before the election. So load shedding, you've seen this. Chiefs and Eagles. I am from Kansas City, so I probably shouldn't talk about the Chiefs and Eagles, but you've been to a sporting event probably, or some other event that there's like a halftime show. Okay, maybe at the Super Bowl you would have stayed and watched the halftime show possibly, but I'm not that kind of person. I got to run to the bathroom. So this is natural load shedding. You notice that it's just Eagles people standing there because the Chiefs fans have all cried every bit of water out of their bodies, so they don't need to be there. So natural load shedding. This is you probably have done this maybe, or seen somebody do it. Like that poor kid there can't even. He's got his legs crossed. The guy in front of him is like, man, this line is long. I'm tired of being here. And you know what? This guy really needs this more than me. So I'm going to hop out of line and go get a hot dog, and then I'll come back. I'll come back in a minute. We'll see what happens. So how can you do load shedding? It's not just throw everything away, right? That would be bad. So we have different things. So on the system that I was working on ePulse, you had the devices that you needed to keep up to date that keep people voting. And then you have all these election workers who are like, hey, I want to run a report in the middle of an election just to see how many people have voted right now. And your servers are being slammed and they want to run reports. So what we did was we walked through and said, hey, if it's a device, we're going to try to do everything we can to handle that request. But if they're hitting endpoints that are running reports and things like that, if the server has an average response time that's a little bit high, we're just going to throw those away. We went through the election. I'll tell you about the end of the election later. Never mind. I'm going to skip that part. The other thing that we looked at was timeouts. We knew that these devices were not going to wait very long for a response. In computer time forever, but about a minute is how long they would wait. And then they say, the server must be messed up. I'm going to request again. Right. So what we did was mark when those times came in on the load balancer, And then when it got to the servers that were handling it, they would check what time it came in. They would check what is my current average response time for these types of requests. And if I'm not going to be able to respond by that deadline, throw it away, because they're not even going to be listening anyway, right? But unfortunately, that's not the only part of the picture, because that just prevents issues, hopefully. But there's always the point where you do have an issue. So that's where recovery comes in. And that's back off and jitter. Who knows what back off is? Jitter? Yeah, there's usually a few less. Yeah. All right, so back off and jitter. Back off. It's my kids again, right? I'm trying to make dinner. They keep coming in, and I don't know how many people have had teenagers, but when teenagers are hungry, they don't know a whole lot of words. And this is the F word at my house. Food, food, food. Not I'm hungry, not when's dinner gonna be ready, just food. I hope that they don't watch this. I'm such a bad dad. And I'm like, hey, go away. Just come back later. I'll have it done. And then they keep coming. I get overwhelmed. And then I'm like, fine, here's a snack. And I spend my time finding them a snack. In the meantime, I've burnt my food. And now everybody's waiting longer. So I need them to actually leave and back off. And that's what back off is. So when you get a bad response from a server, it's backing off a certain amount of time. Typically, what I see almost always is exponential back off. It's like the thing that you're told to do. So you have a base delay, let's say 500 milliseconds, and you multiply that 2 to the power of your current attempt, unless you count with 0 first, that you don't minus the 1 then. So it's an example. 500 times 2 to the 0 is 500. Next attempt is 1,000. Next attempt is 2,000 milliseconds later. Randall, I need math. So yeah, 8,000 milliseconds, and so on. And a lot of times you implement a max. So I'm not going to back off more than 2 minutes or 5 minutes or whatever your system needs. And that's great. It does part of it. But see, you get this kind of graph. So these are requests backing up right after a problem. And they all end up together. Even though these like iPads are all started by humans and they're all started at different points in time, you get this back off, and the server gets a few requests in before it can't handle or everybody's timing out. So they request again and again. There's my little currently away. And again. And these, has anybody heard of the thundering herd problem? Yeah? So this is basically what you're doing is you have a herd of buffalo running at your server and destroying it over and over and over. So your server has a hard time recovering, and you're overwhelming. So what do? Actually, I forgot about this slide. So if you track over time, you have a number of clients that are trying to get a successful request over time. You get this nice little curve where it speeds up at the end as we have less responses, as long as you don't have another problem in between. That graph is deceiving because this is actually quite a bit of lead time. It's really, really long before it starts going up. Nope, wrong button. Oh, also in the past here, I have shut down the monitors by my Keynote slides, so I just decided to completely avoid Keynote this year because I was tired of it flashing on me. All right, so why does that happen? Where's Josh from Olympic? Is he in here? Man, I put this slide just for him. This is for people who drive in the southern hemisphere. This is what it looks like here in the northern hemisphere. So imagine you're driving down the road and you come up to the stoplight, and people pull up behind you. And when that light turns green, so that's your server is halted, like it can't handle anything. The light turns green, everybody takes off with the exact same speed and acceleration. They get down to the next stoplight and they stop again. More people get in line behind them because they're turning onto that road, and they take off with the exact same speed and acceleration when that light turns green. What happens after a while on that road? Can you even turn onto it? That's probably true. Uh, um, so you end up in deadlock. You can't go anywhere. You can't do anything. And that's the spikes that you see. So everybody starts lining up. All of your requests start lining up, because when your server crashes, all of those clients that are waiting get an error at the same time, and then they all back off the same amount of time. And so you just compound and compound and compound the problem. So what do people do? This is often called fixed jitter. I call it +1 jitter because it's almost always 1 second. So what you do is you take your back off time and you add a random amount of time to that, up to 1 second, to try to spread that out. Now, this was 2019, 2020 when I'm working on this, so forgive me, but you have to flatten the curve. That's the whole goal there, right? So I decided to graph that. What does that look like? Well, the dotted line is the no jitter, and with your 1 second, you get, this is super zoomed in. They almost look exactly the same. If you're not zoomed in, you can't tell. Enhance. There you go. Now it's big enough. So it doesn't get you anywhere. This 1 second jitter that almost every system that I run into that has jitter, this is what they're doing. And it gives you almost nothing. So then I run into this a lot. I've never read this in a paper or anything, but I see it. People who recognize that 1 second isn't enough, and they do what I call half jitter, which you take your back off time and you say plus or minus half of my current delay. So if I have a 2 second delay, we'll pick a time between 1 and 3 seconds. If I have a 4 second delay, it's going to be 2 to 6 seconds. So you're slowly spreading that wider and wider the more you have to back off, the more spread out that gets, and you're, again, flattening that curve. So what does that look like? About like this. The humps sometimes get wider and slower, but you have these spots in between where you're handling almost no requests. You're wasting a lot of time on your server. And I mean, I'm sure that the boat in that water is a lot better than in the last water, but you still run into a lot of problems, and you can't get anywhere. So what does that look? I'm terrible at drawing. This is more stair-stepped than hoppy. I don't know what word is for that. Bumpy. But it's still like super zoomed in. You're really close. It helps. It does help. But it's not perfect. So what really is the solution? And I guess here's where it gets hard. Why do you want to back off from that server? Anybody? Give time for the system to recover. Absolutely. So it seems really counterintuitive in a lot of ways, but I call it well-caffeinated jitter. It's actually called full jitter is the official term, I believe. Amazon uses this on all their requests. But I will pick a random amount of time between right now, like retry immediately, and all the way at the end. And anybody have a guess why you would want to do that? Oh, good. You were paying attention to the other slides. Yes. Yeah, so we want to spread out. So like the last one, I didn't even show. Oh, no, never mind. Sorry. My brain's not working. So full jitter, this is kind of what it looks like. You have your spike, everything backs off, and then it starts retrying. And everything gets spread out, and it looks like like you can't even tell. If you graph this sometimes in your system, you will see this really interesting pattern where this is almost like AI, because it will find the limit of your server, what your server can handle at any point in time. It will slowly increase and then slowly decrease, and it'll come in almost, if you were here at NervsConf, it looks like PAL's graphs going in and on the zero line. So you really are trying to maximize your throughput with this. And this is probably the best way to float in the water, right, Bruce? You think? Smooth sailing. And this is what it looks like. You get this like nice, almost straight graph of completion time. It is. I mean, it's not. I would prefer that it just go like this, but in reality, we can't get that. So this was amazing. And with all of this, what happened in the election, the 2020 election. So they had servers behind load balancers. They had servers sitting ready to be shoved in behind the load balancer for when their servers that were there were crashing. And they were up all night for every election. We had to be there before the first polls opened, before the last polls closed in Hawaii. So it was a very long day. But on that day, and they had the biggest servers and the biggest databases that Amazon could give them. But that day, we had 0 downtime. Later, they were able to cut their servers in half and then some. We didn't that year because everybody was still scared. So they saved a lot of money, 0 downtime. I brought a cot into the office, and I just ended up using it to read a book and take naps all day because I didn't have to do anything. We did 0 during the election to keep it going. So that was amazing. Yeah. So smooth sailing. That's what it was. It's beautiful. That's it.